Hello, good afternoon. I'm James Taylor. I'm the Research and Development Manager at Chesterfield Cylinders. And today I'm going to talk to you about the hydrogen storage and supporting safety and enhanced availability through lifecycle management. So, briefly cover the company and the group. We're a UK-based company with a diverse range of markets: defence, oil and gas, power generation, industrial gas, and hydrogen energy markets. The customer base is safety critical and high integrity. CSC is a subsidiary of Pressure Technologies PLC, which is an holding company on alternatives investment market. So, a brief history, and it's quite a long history. CSC were founded in 1897 as a welded steel tube company, and it was bought out in 1906 by the Chesterfield Tube Company. Primarily the product then was seamless steel tubes for defence and commercial purposes, periscopes, torpedo tubes, boilers, but safety critical and integrity applications. CSC then further diversified during war efforts and made transportable tubes, structural tubes and gas cylinders to help kind of the aircraft, freighters and destroyers, submarines, and also transportable tubes to carry hydrogen that filled barrage balloons. And some of those tubes that filled the barrage balloons are still in service today in hydrogen storage 80 years ago. Around 1906 as well, this is where the mainstay of what we do now, which is gas cylinders, tubes and pressure vessels. We started making them for oxygen and carbon dioxide, and then further moved on to industrial gases, hydrogen being one of them. In the 1930s, the heavy tube department were created, and they manufacture seamless cylinders up to 660 millimetres in diameter. An example of this product is one of the early first hydrogen tube trailers that was pre-1950. So, quickly on this one before we get into the more technical stuff, is we've been designing and manufacturing cylinders, tubes and pressure vessels for over 125 years. This has been global and covered many different jurisdictions. We offer ongoing technical support for the life of the product, whether this is technical advice or through lifecycle management. We can do that either at our facility or offered globally in situ by our integrity management team. So, quickly, what is hydrogen storage? Many of you already know, but hydrogen storage is integral to supporting the hydrogen supply chain, from manufacturing to transport to point of use. Typically, Type 1 static storage pressure vessels are used as ground storage. Working pressures depend on application, but vary between less than 200 bar to 950 bar. Type 1 steel transportable cylinders and tubes are the virtual pipeline between the manufacturer and the point of use. They also can be the point of use with offtake straight from them. They typically range in pressure again, probably up to kind of 200, 300, 400 bar for Type 1, and they could take the form of individual pressure receptacles or form part of bundles, MEGCs or battery vehicles. As can be seen here, ground storage on the top picture and tube battery vehicles for the bottom two that are in service currently. So, designed for through-life safety. Type 1 steel cylinders have been used for the storage of hydrogen for well over 100 years. The product has developed greatly over this time, becoming more efficient with processing, non-destructive examination and metallurgical advancements, but the designs always come from international, European and national codes and standards, with storage of hydrogen primarily as their focus point. Things like ISO 11120, AD 2000, ASME Section 8, Div 1, Div 2, and these have always been developed by experts with decades of experience and product data from in the field. But crucially, what we do is we marry up with design optimization with through-life inspection and maintenance at hand. This gives both a unique skill set, which gives some hydrogen storage systems over 80 years in service. So as can be seen, one of the members of our team carrying out inspection on an offshore platform, doing visual inspection on a crane. So, managing fatigue and embrittlement, which is a topic that's always brought up. So, as with most materials and cyclic loading, Fatigue is an issue, and coupled with hydrogen embrittlement, it can be accelerated. So we had product in service for 80 plus years. Essentially, it's engineering. Embrittlement can be effectively and safely managed. This is done by evaluating and qualifying the product with hydrogen service in mind, not only through codes and standards, but by utilising decades of product's experience and data. Typical causes of embrittlement are stress raisers such as notches, high stress designs and features, and also the material microstructure. How we mitigate this? So we use low stress designs and geometry. These reduce the stress concentration areas and therefore potentials for propagation. Seamless, smoothly transitioned, integrally forged product means low stress, and no welds means no heat affected zones. Internal surface finish, we go above and beyond the quality dictated by the standards and codes to eliminate any stress raisers. NDE advancements such as UT and AET, which we'll come on to later, allow finer imperfections, possible defects to be detected, quantified and removed if required. Chemical analysis and material properties. So I say all the time. And microstructure can be tightly controlled, utilising standards such as Quad 1.4 Part 1, which is compatibility, for example, of cylinders and valve materials with the gas contents. These have been developed again through decades of experience. Fatigue analysis is undertaken. Again, this is generally conservative because the calculations are always based on propagation and growth rather than initiation. We strive to eliminate any potential sources of initiation at the design and manufacturing stage. And then by tying this in with periodic inspection and test regimes, it allows any potential issues to be caught in their infancy. So what makes Type 1 optimised for hydrogen? Essentially, steel is versatile and manages temporary variations. Steel can be rapidly filled and discharged with hydrogen and still be below the creep range created by the transient temperatures from the gas expansion and compression. Not only is this beneficial for product utilisation, allows better efficiency of use, but it also allows pulse purging for gas purity, and that can either be done at commissioning or being re-entered into service after inspections. This reduced downtime and the product life cycle and its maintenance periods. So as you can see, a typical installation for hydrogen static storage at a refueling station. So, crucially, what makes this product last so long is periodic inspection and test. Periodic inspection and test can be overlooked by operators, but these are critical to the prolonged, continued and safe use of the product. They assess the condition of the product and its ability to continue in service. The inspection and test can be done at the facility or in situ, where the product is sited, and this can be done globally by our management team. To underline the importance of periodic inspection and test, we promoted and worked on British and European standards for in situ, non-destructive examination and testing of products in service, in particular where it's not sustainable to remove the product. One of the main focus points of this is acoustic emission testing. Now, AET is a tried and tested technique. AET works by using specialised equipment that turns acoustic emission, the ultrasonic sound waves generated, into electrical signals that come from energy release, such as a crack propagation or formation. This is particularly suited to monolithic, homogeneous structures, such as steel tubes and pressure vessels. This is typically achieved by placing sensors at the end of each tube and calibrating the equipment using very sensitive kind of sensors. So they'll even detect 0.5 millimeter pencil lead break in the length of a 12-meter tube. We usually pressurise to 110% of the operating pressure, and this overcomes the Kaiser effect and puts the material into a stressed area where it's not being used operationally. This will allow any defect, if it is there, to propagate and be seen. Its particular advantages are allowing the inspection of the products in situ and potentially using the medium that's in them. This reduces downtime and it maintains hydrogen purity and eliminates any cross-contamination. And it can detect crack formation and propagation in difficult to access areas, and crucially in its infancy, before it generates into any kind of defect that would be problematic. So as can be seen on the top pictures, you've got acoustic emission testing, and then on the ones are ultrasonic testing. It's been done in-house. So crucially, we optimise our product designs with our customers, operators and authorities to integrate periodic inspection and test in inspection intervals with fatigue cycles and plant maintenance periods. When combined with in-situ testing like AET visual inspection, it increases cost effectiveness, plant availability and reduces downtime, bringing the overall OEE up. Some inspectors and testing can be carried out while the product is in service, further increasing the equipment's uptime and keeping plants and virtual pipelines running for longer. This makes the product very sustainable. So, sustainability. Steel is sustainable and goes hand in hand with the goals of a sustainable future. Type 1 steel is cost effective and efficient for the storage of hydrogen. Steel is sourced typically for us of European origin, low CO2 mileage footprint, and production sites being based in Europe with strong decarbonisation strategies as the EU targets net zero. The proven longevity of Type 1 products, with some reaching over 80 years in service. And also, steel is 100% recyclable. When it's reached the end of its operational life, it creates a circular economy. It will be melted down essentially and made new storage vessels once again. This reduces the customers' and the economy's footprint. Total cost of ownership. So, by utilising Type 1, TCO is reduced in comparison to other technologies. By optimising the storage from the outset, back to fatigue and embrittlement, the low stress designs, fatigue analysis, periodic inspection and test, and optimising for customers' maintenance periods, not only is the usable life of the asset increased, but so is its utilisation, and crucially, the operator's uptime. This can drastically offset the capex with a reduction of OPEX compared to other technologies. And also at the end of its life, there will usually be a residual value in the scrap before it is made into new vessels once again. So, in summary, Type 1 steel products can provide decades of utilisation through effective technical design and life cycle management. In situ periodic inspection and test and recertification examinations increase operating efficiency and operators' plants uptime, and it provides a circular and sustainable economy. Essentially, thank you for your time. If you have any questions, we're located at B64, the Chesterfield Cylinders site, and I want to thank you for your time. Cheers.